Hello. In the previous video, we study orthogonality, we study orthogonal basics, orthonormal basics, right? And we also discussed the importance of orthonormal basics. Let me remind you about that before we move to this topic, how to make an orthonormal basics from any basics of a vector space, okay? So, orthogonal, orthogonal, and orthonormal basics. Okay, so if we discuss about orthogonal means any two different vectors are orthogonal. So I will write vi, and then if we write in the language of inner product, so vi times vj equal to 0 when I is different to j. That is orthogonal, right? So orthonormal includes orthogonality. So we have the first condition in here, vi, vj, in the product equal to 0 for I is different to j. But at the same time, we require that the norm of each vector is 1. So basically, that the inner product of each vector on with itself is just 1. So we need two conditions, A and B, right? And here we just have A. So from here, in order to make an orthonormal basics, we need to make an orthogonal basics first, right? And then we move to the second step to make an orthonormal basics. That is the first thing. The second thing about the importance of orthonormal basics. So I think we discussed about the following theorem. If you have an orthonormal basics vi, orthonormal normal basics, right? Then you can express, then for any w in the vector space, you can express w as w in the product with v1, and then v1 plus w in the product with v2, and then v2, and so on, and then w, vn, and then vn. So basically, these theorems say, yeah, in order to find coordinate of w, you just need to find inner product of w with each vectors in that orthonormal basics. And that is the importance of orthonormal basics. All right, now let's discuss about, how to make an orthonormal basics, right, from any basics. So let's see the following idea. So we are talking about Gram-Schmidt autonomalization process. Look at this. So here you have only two vectors, right? Suppose you have, and here they say, yeah, v1, v2, vn. But let's start from just v1 and v2. So that means let's talk about R2, okay? So I have the following picture with R2. Suppose I have two vectors like this, that is u, and another one is v. Okay, another one is v. They are not orthogonal, and they are not collinear, so they form a basics of R2. Okay, now I want to make an orthonormal basics, but of course, as I mentioned previously, we need to make an orthogonal basics first, right? So I fix u1, or if you want, you can fix v. It's not a big deal. So I fix u1, I put that as u0. So how to make an orthogonal to u from v, right? Of course, that is the things. So just take the perpendicular, right, straight line, right? And that is pretty simple. But somehow we have to relate to to v. Okay. So here's the thing: we learn orthogonal projection, right, of one vector onto another. So I would say yes. From V, we can find orthogonal projection of V onto U, right? It's not really good, right? Let's find orthogonal projection of V onto U. So that is orthogonal projection of V onto U, right? And then this vector, or this vector, right? They are equal, okay? They are equal. That is nothing but V minus orthogonal projection of V onto U. And of course, this guy, like I denote by U1, the U1 will be orthogonal to U0. So from here, you already have an orthogonal basics, right? So I write this. The first step, I fix U0 and I denote by U0, just equal to U. The second one, I move to the next vector, which is V. So I will make U1 as a V minus orthogonal projection of V onto U. So basically, what does the second identity says about? It says, yes, in order to make an orthogonal vector, you just subtract the second vector by its orthogonal projection on the previous one. Make sense? So this is orthogonal projection on the previous one, which is U, right? Or U0. And then you subtract your vector V from your vector V, that orthogonal projection. So you get a orthogonal component, right? So after that, you want to make an orthonormal, no problem. You can normalize them, right? Orthonormal. You can normalize them how? You just divide, U0 over norm of U0. And then you divide U1 over norm of U1, right? So you have orthonormal basics from U and V. That is the picture for R2. And that's what you can see from here. You fix one vector, and then for the second one, you just subtract from the second one, from the second original one, right? By its orthogonal projection. And that's how orthogonal projection can be calculated. That is, that is nothing but, this part is nothing but orthogonal projection of V2 onto W1. Make sense? Onto W1. They denote by W1, and then, they discuss about W1. They don't want to use V1. I'll tell you about this right later. If we move to three-dimensional or maybe higher dimensional case, so you see why we just talk about W1, W2. We don't talk about V1, V2 in this situation. Okay, so let's move to three-dimensional case, and then we will see. Now we try to discuss the idea, okay? And then after this, we will do different examples. All right, now let's discuss about R3. Let's say R3. So I have R3 like this. This is my X, this is Y, this is Z, right? If I have some three vectors, let's say, you just give me three arbitrary points here. The first point is, V1. The second point is V2, or the second vector is V2, and here is V3. And I want to use the same idea. So firstly, I have to work with V1 and V2. And how? We just use the idea from R2, right? So I will fix U0 equal to V1, let's say this, right? And then I will make U1 equal to V2 minus orthogonal projection of what? Of V2 onto U0. Okay, so we already have two orthogonal vectors, U0 and U1. And now how to make U3? How to make U2? Of course, we have to start from V3, right? But now you see how to work with V3. If you look at this picture, so each point here will have three components, right? For this vector, you can find orthogonal projection of X onto the Z. You can find orthogonal projection onto the Y. And you can find orthogonal projection onto X. So basically, each vector V, let's say V1, each vector A1, A2, A3, where A1, A2, A3 are orthogonal projection of A onto X, Y, and Z. You see, that means A has three orthogonal components on each A6. Makes sense? So we use the same idea, but in this situation, the first A6 is U1, the second A6 is U2, right? So the orthogonal component, of that vector on the third one. So that means you take this vector, v3, you take vector v3, and then you subtract from this vector x orthogonal components on previous two vectors. On previous two vectors u0 and u1. You see, we don't talk about v1, v2, right? On previous orthogonal vectors u1, u2. So I say, yeah, that is v3, and I subtract from v3 the orthogonal projection of v3 on u0 and orthogonal projection of v3 on u1. And then at the end you get vector u2, which is orthogonal to u0 and u1. Makes sense? So kind of you can say that is how to say, parallel pivot law. Parallel pivot law, where this is diagonal. So if you just convert this, the third identity, right? In another form, you have v3 equal to u2 plus orthogonal projection of what? Of v3 on u0 plus orthogonal projection of v3 on u1. So that is nothing but, I just tell you previously, the diagonal, right, equal to sum of three components, right? If we use parallel pivot law. Make sense? So that is the whole idea. If you move to higher dimensional case, like if you have one more v4, so you do almost the same thing. You have u1, u0, u1, u2, and then you can make u3, which is equal to v4 minus orthogonal projection of v4 on u0 minus orthogonal projection of v4 on u1 and minus orthogonal projection of v4 on u2. And then you can generalize this to any n. Make sense? So that is the whole idea of so-called Gram-Schmidt orthonormalization process. And this formula is written in the form of inner product. But if you pay attention, this is nothing but orthogonal projection of, let's say, v3 on w1, and this is orthogonal projection of v3 on w2, and this is orthogonal projection of vn on w1. You see, just subtract, right? You subtract the last vector from the last vector x orthogonal components on previous orthogonal vectors, and then you get an orthogonal basics from v. And then once you get w1, w2, and wn, you can normalize all vectors to get orthonormal basics. So you get this divided by the norm of w1, w2 divided by the norm of w2, and so on, wn divided by the norm of wn. And that is your orthonormal basics. That's it. Okay. All right. Let's move to examples. Okay. I will skip this because that is, we just accept, like, yeah, if you do that, you will not change the space, the spending, the space spend or generated by v1, v2, vk is just equal to u1 equal to the space generated by u1, u2, uk. Okay, where ui is where ui's are unit vectors, right? Unit vectors wi divided by the norm of wi. Here's an example. They ask us to apply the Gram-Schmidt process to the basics B uh, to find, orthonormal basics. Okay. All right. So how do that? They fix W1, you see, and they denote by W1 just V1 equal to 1, 1. Okay. And then they will find W2. How? They will subtract from W2 the orthogonal projection of W2 onto V1. Right? That is the formula of orthogonal projection of V1 onto W1. So they calculate this, they get 1, 0, and subtract this, and they get negative 1 half, 1 half. Okay, so if you want me to do computation, okay, no problem. Let me do this. Let me find the orthogonal projection, right? Just try to verify what they did in here. So the orthogonal projection of V2 onto V1 is equal to V2 inner product with V1 divided by the norm of V1 square. Okay, and this is V1. The inner product in this case just dot product, so I just get 1 in here divided by the norm of V1 is 2 square but square. Okay, and here 1, 1. That's why we have 1 over 2 and 1 over 2. Okay, wait. Yes, that is orthogonal projection. It scares me. And that's what we get in here. This is what we get in here. 1 half. Okay, and then you take V2, which is 1, 0, subtract 1 half, 1, 1. So you get negative 1 half and 1 half. And that is your W2. Okay, and then the next step, they need to find, the norm. They need to find the norm of W1 and the norm of W2. And then they make U1, U2 by dividing W1 by the norm of W1 and W2 by the norm of W2. And they get 2 vectors. These 2 vectors are unit vectors, and they form an orthonormal basics of R2. All right? So I think you can verify all this computation easily. It's not a big deal. Let's move to, I hope that I have an example for R3 in here. I know they just say, yeah, this picture just explains about that. About, the picture of unit vectors in here. So basically they have the first vector, which is, 1, 1. The second is 0, 1. They want to make an orthonormal basics. So this is the unit circle. That is the unit circle in here. Unit circle, right? So they want to make that. So, any point, 2 points in here, you see? On the unit circle, you pick any point, right? 2 points in here, and then they are orthogonal. So exactly they will form an orthonormal basics. All right. I see. Let me see if they have more general situation. For example, in R3. Okay. Let's consider this problem. Find orthonormal basics for the solution space of the homogeneous system. That means we have to solve these systems, right? We have to solve this system. So the system has two equations with 4 variables. Okay, it's fine. We can make that. So let's write this in the form of matrices. So I divide into 2 parts. So we have more place for this. The matrix form looks like 1, 1, no x3, 7, x4 in here. And then 2, 1, 2x3, and 6x4 in here. So you have 0, 0 over there. Okay, usually we don't write it, but it's fine. Then, from here, I want to make a reduced row echelon form. So I need to multiply the first row by -2, and I add to the second, right? So I have 1107 in here. Let me ignore 00 because they don't affect. On the system, I get 0 in here. 1 with -2 is -2. Add to this, I get -1. 0 is still 2 in here. -2 is -14. 14, -14 plus 6 is -8. Okay, and now we want to multiply, just add the second row to the first row. You have the reduced row echelon form right away. So you get, I'm sorry, you get 1 in here, 0 in here, 2 in here, 7, not 7, should be -1. You have 0, -1, 2, -8, right? You just add the second to the first row, you get that. And that is already a reduced row echelon form, right? The rank is 2, so you have 2 free variables in here. I can write a solution. x1 equal to -2x3 plus x4. x2 is equal to -2. No, it should be 2. When you set this equal to 0, right? So that is 2x3 minus 8 x4. Okay, and then we have x3, x4 as free variables. So the general solution looks like -2 x3 plus x4, 2x3 minus 8x4, x3 and x4. Okay, so you can find the basics right away. I can write that as x3 -2 2 1 0 plus x4 1 -8 0 and 1. I just separate x3 and x4, right? All terms with x3 in one vector and take x3 out because that is common. And then you have this. So basically, we already found 2 vectors in the basics of the homogeneous systems. They are here. Okay, they are here. The first one and then the second one. They ask us to find orthonormal basics, right? For the solution space. You see? They ask us to find an orthonormal basics for the solution space. So that means we have to apply the Gram-Schmidt process to these vectors, right? For these 2 vectors. Okay, so we just fix one. Let's say that is U1, or you can write V1, or this is V2. So I will fix the first vector. I denote by U0 equal to V1. And then the second vector is U2 equal to V2 minus orthogonal projection of V2 onto U0. Okay, so the orthogonal projection, okay, let me write. I have U2 equal to V2 is 1 -a 0 and 1, and then minus I have V1 dot product with V2 would be, and here time U0 dot product is -2 equal to -16, and then plus 0, which is good, and divide by the norm, but the square of the norm would be 2 square plus 2 square plus 1 square. Okay, so let me check it. So -2, that's good, and then -16, yes. Let's solve this, and then we have solution in the next slides. Okay, I just try to work out for you. So that is 1 -8 0 and 1 minus plus. I write plus because we have negative, right? Negative with minus over there. So I have 18 divided by 4 with 1 is 9. Looks good. And 0 1 is -2 2 1 0. Okay, So I have 1, negative a 0, and 1, 18 over 9 is 2. And then let's do 2 with negative 2 is negative 4, 2 with 2 is 4, 2 with 1 is 2, this is 0. And then we have, just subtract them, 1 plus negative 4 is negative 3, negative 8 plus 4 is negative 4, 0 with 2 is 2, 1 with 0 is 1. So basically, I will have two vector. Uh, my bad. We will write u0 and then u1, not necessarily u2. Okay, so we have this vector and then this vector. They form an orthogonal basis, and now we need to normalize them. That means just divide each vector by their norms. That's it. Okay, so that's how we can solve this problem. You see from here, let me check this, the solution. So the augmented matrix for the system look like this, and then they get the reduced row echelon form. Okay, let me see if we have the same or not. Yes, we have the same, I guess. Yes, the same, yes. The only thing different is, they have 1 negative 2 in here. We have negative 1, 2. It's okay. And then they have two vectors like this. Okay. So they separate, they say S and T, that's 5. We just keep X3, X4. They separate them, and then they use, the B, V1, V2, that's two vectors. And then they fix the first one. In this situation, they divide, V1 by the norm of V1 to get a unit vector. I will tell you, why, right? But let's finish this and see. And then, they apply this process to find another vector, W2. And then they divide W2 by the norm of that. They get, what they need. Here's the reason. Let me explain you. Here's the reason they want to divide. They want to make U2 as a unit vector. If you pay attention, this is unit vector, right? This is unit vector. And since U1 is a unit vector, they can make V2 easier. So the orthogonal projection, you see, actually, that is almost the same. But in the orthogonal projection formula right here, they don't have to divide by the norm of U1 because the norm of U1 is already 1. Make sense? But in my experience, we don't have to do that. We don't have to do that. If you do that by hand, you have a mistake with fractions in here. So I very encourage you, try to avoid fractions during the computations, because if you do wrong in one step, the whole problem will be wrong, right? So you just need to find orthogonal basics, and then at the end you will normalize them to get an orthonormal basics. Okay, all right. So that is all about this. But since they don't have any problems with 3-dimensional case, I would like to give you one more problem. Okay, let's solve that out, and then we'll see how that works for three vectors. Let's say we have V1 is 1, 0, 0. V2 is 1, 1, 0. And then V3 is 1, 1, 1, which is very easy example and easy vectors. Okay, so I want to get an orthonormal basics from here. Okay, of course, they are not orthogonal. You can check, the dot product of V1 and V2 is just 1, not 0, and with V3 also 1. So they are not orthogonal. I want to get an orthonormal basics. And of course, these three vectors form a basics because they are linearly independent. you put them together, right? You get a matrix, a triangle matrix right away. The rank is equal to 3. So I'll fix U0, that is V1, which is 1, 0, 0. Okay. And then I will have U1 as V2 minus orthogonal projection of V2 onto U0. So that is 1, 1, 0 minus, let's find orthogonal projection of V2 onto 0. So that is the product of, let's say, U0 and then V2 divided by the norm of U0 square times U0. You can see the dot product of what? Of U0 and V2. The dot product is just 1. You can see that from there, the definitions, right? And the norm of U0 is just 1 too. So basically I have, that is 1, 1, 0 minus 1, 0, 0. So I get 0, 1, 0. That looks good, right? Okay, so now I will have another vector u2 equal to the last vector, subtract orthogonal projection of v3 onto u0 minus orthogonal projection of v3 onto u1, and we just need to find them, right? v3 is 1, 1, 1. Orthogonal projection of v3 on u1 is v3 times u1 divided by the norm of u0 minus v3 times u1 divided by the norm of u1. Oh, here I think I mix u0 and mix u1 in here. Okay, so that is 1, 1, 1 minus, I think you can check it easily, because if you, this is u1, right? So if you multiply with 1, 1, 1, you get 1. So I have 1 in here. The norm of u1 is also 1, so I have 1 over 1, 0, 1, 0 minus, and u3 with u1. Oh no, I just calculate this one. Oh my goodness, that is 1 over 1, right? And then u1 is 0. Okay, this is the one I just calculate. Okay, so for this term I would calculate this 1, 1, 1 with, okay, let me draw. I get 1, 1, 1 with what? With 1, 0, 0. Okay, that's also 1, right? So this is also 1, and then the norm is also 1. I get in here would be 1, 0, and 0. You see? So finally I get 1, 1, 1 minus 0, 1, 0 minus 1, 0, 0, which is 0 and 0, 1. So you already have 3 orthonormal basics, because they are just 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this easy example just shows you, how this process works, right, for 3 vectors. So I hope that the video is clear enough. But if you have any questions, please feel free to let me know. All right. And on Friday I will do review for the whole 2 chapters, and I will have a practice test for you, and we'll write test next Friday. Next Monday. All right. Bye bye.